Welcome to Thermodynamics. Got a test coming up on lab time Thursday. That's so exciting because you can show me what you know. Oh boy. Any show of hands, how many people would like to know what's on the test? Okay, a few of you. All right. For those of you who are curious, there's basically two parts to it. And sort of, I'm going to say one part is like system efficiency. What does that mean? Do you remember these? We had these little diagrams, and we had like some heat that went in. It went into this magic box, and on one side of it you got work, and on the rest of it you got there's Q high, Q low, or in and out, what have you, and work. This is the network that got that. There might be some work that went on inside this box. This would be an entire like power plant, for example. And I might give you something like there's network done, there's Q in, Q out, and there's efficiency. Given any two of those things, you should be able to find the rest of them. Because if I give you efficiency and what came out, that's actually one of the harder ones. Let's do something else. If I give you efficiency and the net work, well, efficiency is defined as, well, what is efficiency defined as? Yeah, for heat engine, Q in is what you paid for. Not Q out. That's your exhaust. Unless, like, if a hot exhaust pipe is what you want in your car, then that would be measure your efficiency on how hot the exhaust got. But usually it's about going down the road. You don't care about the exhaust really. So that's the net work. That's going down the road, and this is your exhaust pipe, or the radiator, or whatever. So what did you get? You got the work that was converted. What did it cost you? It's the fuel you had to buy. So that's this. So if I gave you, and so, you know, so you can unbutton this thing because they're all related. I could give you any two of those things. I could give you Q in and Q out. You can tell the efficiency. How would you do this? Because of conservation of energy, the net work would be the difference between those two. And if you knew what your Q in was in the network, now you've got efficiency. So get familiar with that sort of stuff. I'll be giving you two of these, and I don't honestly recall right offhand which two, but at any rate, two of those characteristics, and you should be able to walk your way around this. There will be a little diagram. I'm looking for something. There's a box, and inside that box, I'll be looking for a diagram with this stuff on it, and then the numbers that go with it from the problem. So a graphical, I mean, you can answer the questions and get the right answer, but if you don't know how to put it in the box, that's sort of a conceptual, how's this all working thing. And another thing on the efficiency, what is Carnot efficiency? Anyone recall? Yes, it's about temperature. 1 minus low over temperature. It's all about temperature. A Carnot engine was one type of a conceptual reversible engine. And a reversible engine is isentropic processes in like compression and whatever. There's isentropic process which we can calculate that we'll never actually get to, but that's a limit. And any reversible engine will be as efficient as any other reversible engine because they're all 100% efficient. But there's thermodynamical limits to how much energy they can convert. So this is essentially the best efficiency we can hope to have. The whole thing about entropy and isentropic processes, if you came up with an efficiency here of 25%, and the process here, Carnot efficiency said you had 50% efficient. There's a difference between these two. So there's sort of the overall efficiency, including this limit, is built into here, and you have a chain of efficiencies. This is probably, I'm talking too much now. I probably confuse you, but I will say, basically, this is like an isentropic efficiency. It's the perfect case, the best you can get. And then there's a mechanical efficiency that's how you're losing efficiency due to the reality of it. And if you multiply the Carnot efficiency times the mechanical efficiency, you get this one. So this was 25% efficient. If this was 50% efficient, then if you had 50% mechanical efficiency, 0.5 times 0.5 gives you 0.25. There's a chain in there. One of them is this isentropic efficiency, which is essentially what this is. And the other one is an efficiency. How efficient are you relative to that perfect one?
And so that would be like including friction and stuff like that.
The friction and losses you get because there's swirling going on and there's frictional fluid pressure loss and all the other stuff, just all bundled together. So there's sort of a chain of efficiency. This is the limit, and then you're only 50% as good as that limit. That's what the isentropic process is about, which gets us to the next problem, which is all about a steam turbine. And steam turbine, I'll draw a little TS diagram on it. Here's my saturation dome. Steam turbine, it comes up to its whatever pressure you have to its boiling temperature, and then you turn from vapor into or from liquid into vapor at that temperature and pressure, and then it starts boiling some more, goes superheat. And I'm just talking about, I'm going to have there's an isentropic turbine, and then there's, so here's state 1, here's state 2s. We can find this using tables. How do we do that? If state 1 is an entropy value, this magic thing about entropy tells us where, when we get to the new pressure is what's real. When we get to the new pressure, the outlet pressure, what's the quality going to be? Is it in saturation or superheated? That's all about finding an isentropic process, finding where that entropy value lands down here. So if I have an entropy value of 6.1 up there, if I find 6.1 on the chart down here, I might have to interpolate. And then if I have a process that has an isentropic efficiency, this is the amount of the difference in enthalpy, which is all we ever really care about. Enthalpy there to the enthalpy when we find this state. Using entropy, we find the state, and then knowing that state, we find the enthalpy value for it. So entropy finds it, enthalpy is what we're looking for. That's the total amount of energy available to be converted. If we discovered by testing that it's 90%, converted 90% of that energy to work, then that's a 90%, a 0.9 isentropic efficiency. So You have three states you have to deal with: 1, 2s, 2a, p, c, h, s, and maybe an x. There'll be a table to fill out, sort of like that. And S2s equals S1. And that means work 1 to 2s. How much work is done? H1 minus H2s. Work from 1 to 2a is only going to be H1 minus H2 actual. Solving for that's how you find this one. From that property you find, when you find this state, whatever the quality is, and whether it's in saturation or wherever it is, if you find this state, then from that state you can determine what enthalpy goes with it. And that's this ideal state. That's the magic in the thermodynamics, is knowing that this is a limit. So whatever S1 is at its temperature and pressure, and what you'll be given generally three things will define the cycle, the ideal cycle: pressure and temperature at the top, and pressure below, especially if it's in saturation. This is the amount of energy that's available to be converted, and this is how much actually got turned into work. That's what the isentropic efficiency comes about. This isentropic value just tells us, if we had an isentropic turbine, all this would be turned into work, but it doesn't happen. That's what it will limit. So, I'll be looking for this number and that number and filling all this stuff out.
So you'll be looking for the difference in enthalpy.
Yes.
And the rest of the chart below?
Yes. Okay. And usually you fill out the chart that tells you what do you know, what you need to go looking for. This one, the top line for sure is probably going to come straight out of the superheat table. The second line, I try and make it so it's not like totally crazy. I mean, usually try and find a place where it comes down and you don't have to do a whole lot of interpolation, but you might have to do some interpolation to figure out what the quality is. You might need the quality to find this value. It's probably going to be in saturation, and then X quality tells you how far it is from liquid to vapor. So I guess I should say let me draw it like this. You use the entropy value to find X. Use the X value to find H. That's really how that works if you're in saturation. Does that make sense? Kind of what we're going for here. I don't recall if I had you draw it out like this. There might be the TS diagram. This doesn't show, but isentropic means same entropy value. So whatever the entropy value is at the top, it's the entropy value at the bottom. So on a TS diagram, same value means straight up and down.
So are you wanting us to find the actual entropy value using the X?
Like
Yeah, that
this one here? Don't recall. Maybe not.
Yeah.
But you know, this is what really matters for trying the work done. Doing that, you could find X from this value, and then you know that basically you're going to have a higher value of X because entropy always increases in processes. You see that number increase. I think one of these, I'm pretty sure that was the one I marked. Don't need it, don't care. That we need entropy to find this, so we can find that. But down here, it's academic interest. During the test, we probably aren't into academic interest. We're fully engaged with everything else. So that's basically what it's about. I think one of the seems like I'm pretty sure one of the parts is find X2S from S. If I recall, the parts of the problem were fill out the table, but you can't really fill out this value until you have this, and you need this to get that, you need that, so you can get this, and then with this you can solve this equation essentially. So oh, wait a minute, I wrote that. I wrote something wrong there. Time to correct. H1 minus H2S times the efficiency gives you the work from 1 to 2A, or that's H1 minus H2A. That's how that works. I'm sorry. This is the amount of energy available to be converted. 90%, if that's 90 of this value would be how much got done, but that's also H1 minus the H2 actual output. So I screwed up that. Efficiency times the energy available equals energy converted. Crucial mistake there. So, any questions on that? Yes.
Are we drawing the TS diagram?
I believe I think I did put a box in there for drawing the TS diagram, and it doesn't have to be, hopefully you get it a little more vertical than I got it. It's just a conceptual thing. I'm pretty sure that was in there. I like the things that are, you know, sort of the visual conceptual. This is like a free body diagram for thermodynamics, if that makes any sense. I think that's in there. And it doesn't have to look a whole lot different from, if I was labeling the points. If this came out of the saturation curve, the temperature would rise. It's the same pressure, and if it was out of its saturation value, then it would be out here somewhere, and your 2A would be up a little bit. That's actually probably how you'd use it to measure output. set it so it comes with a really high value here, and then you can measure the temperature pretty easily. It's really hard to measure quality. You can calculate it, but to actual measure, how thick is the fog at this pressure? That's hard to measure. Okay. Any other questions on that whole process? I find that using tables, when you start getting these properties, when you're walking around a cycle or between one process between two states, setting up a table like this helps you clarify the mind. What do you know? What do you need to know? Which number went where? That's like engineering is all about problem solving. Even they'll hire you to do things that are unrelated to thermodynamics just because of the concept of what do I know? What do I need to look for? I got an answer. Where does that go? Which box? That sort of thing. Just this sort of problem solving technique of what do I know? What am I looking for? You can get jobs just because of doing that kind of thing, and it's really helpful from now through the rest of the class, because we're going to start going into engine cycles next in like a minute here. When we start working problems there for steam and for this air standard cycles, it's all about state 1 is what, state 2 is what, state 2S, 2A, which one are you looking for, what do you know? That's how our analysis will work. Okay. Let's see. There's a problem for the, we'll do the Otto cycle example. I'm going to talk through some of the others and we'll come back to do the examples. But well, maybe I'll start. Got a minute here to start the setup on it. But I'm not going to take the time to finish it right now. If you do this on a pressure volume kind of a diagram, problem like this, set up a table and have state P, V, H. Don't even care about S because we're not going to have a table to look it up on. But we'll put A, S just to track it. Again, the Otto cycle is spark ignition, otherwise known as a gasoline engine. State 1, pressure is 1 atmosphere. Oops, not V, but I want a temperature. And we have a compression ratio is about volumes. So V1 over V2 is how much it compresses. for ideal gas, what this means is to find this state, these properties, we just take the ratio of pressures to the ratio of volumes, however that works, and apply one of the formulas that has exponents with k's in it, because that's been developed from an isentropic process. So H, and I'm going to call this the lowest energy point. That's going to be my reference. I'm going to just call it 0. And the work of compression is going to be H2S minus H1, which is really going to be C sub P times T2S minus T1. So if we can find T2S, life is good. And we need a formula for that. And we'll look at that a little bit later. Usually they're going to give you the temperature. They're going to give you the inlet condition. It was sucking in atmospheric air usually. They're going to tell you maybe, either they'll tell you one of two things. They'll tell you, here's how much heat went in, and you got a certain amount of air, and you put a certain amount of fuel to it, and you burned it. So heat jacked up the temperature, and go find the temperature. Or they'll tell you, here's the temperature. But actually, if they just give you the heat, and it depends on the givens, and I didn't have that written down here, but the Q in conceptually in this diagram, the pressure times the change in volume is the work that's being done. The work under here is the work that went into the compressor. The work at the top is the work that came out from the piston pushing. And the difference between the two of them is how much you get to take out to the shaft, conceptually. The heat that was in is what drove it. The heat was out was our exhaust. So, and notice these are both happening at constant volume. So, what can I say? The Q in would be H3 minus H2S, which would be C sub V times T3 minus T2S. All about change in enthalpy, but enthalpy, well, in this case, it's constant volume. It uses C sub P. There's no work going on, so we'll still call it enthalpy. If it's a constant volume, the pressure rose, but that's going to be part of the internal energy. So we can use the C sub V value for this one. It really ends up being a change of internal energy because there's no change in work if it's constant volume. Everybody we can use this, if they give us this value, we can use this relationship to find the high temperature. Or if they give us the high temperature, we can use this to find the Q. We need to know one of those two things. And that would have to be the Q per kilogram for that to work. So I think that should be a little Q. Otherwise, we need the mass to scale it. Work of the power stroke is going to be H3 minus H4S, which is C sub P now, because it's in motion. There's going to be work going on, times T3 minus T4S. Well, that's great. The only way we find this is because it's an isentropic perfect process is a point of reference for us. So we need a formula to find T4S. And exhaust energy is H4S minus H1 equals C sub V T4S minus T1. That should wrap it around. There's these two things we have to, there's these three calculations. And there's no interpolation, by the way, going on here. Life is good. I summarized some of this in a reference for you, but a lot of this is coming out of the last chapter, at chapter 8 for ideal gas. I guess I should do it like that. Remember, this is a ratio of volumes. So based on those isentropic relationships, ratio of volumes, T2 over T1 equals, or V2 over V1 to this power equals T2 over T1. And I just solved it for the T2S. And this is the same, only now we have to invert it. 4 over 3 equals, good idea. So that's how we, if we had the numbers for this, and I don't have them right now, so I'm not going to push this farther, but with this value, we could plug in here with C sub P, and it's an air standard cycle, so you use the values for air. You could get, 1 was 0, because that's our lowest value point. We're just going to call it our reference, so we don't have to subtract some odd number. That's basically going to tell me my value for H2S. We know the heat value that went in. We know this, we can solve for this. Now we got T3. If we have T3, we put in the expansion ratio and we get the T4. And with C sub P, we get the amount of work done. We know the difference between these two values. That's the net work. This is how much it cost us, and now we got an efficiency. So, I'll get numbers for that next time. let's look at another engine type. What if we got a gasoline? If you have a high enough compression, you run into this pre-ignition problem. It starts to burn before it gets to the top because when you compress something, it gets hot. What if you can compress it to the point where you don't need a spark plug anymore? Well, it's called diesel. It's called compression ignition. And next time, if I remember, I'll get out my compression igniter. You put a little piece of toilet paper in a glass tube, and it has a piston. You go like this, and toilet paper turns into smoke. It actually works. My car, I have a diesel car, and a number of you probably have diesel trucks and tractors and whatnot. The difference, and there's a couple of reasons I think why diesels are more efficient. If you have a car that gets 30 miles a gallon, the diesel's going to get 40 miles a gallon, for example. That's why you don't see gasoline-powered big rigs. Try and find any large truck that's gasoline-powered. They're all diesels because it saves a lot on fuel. One reason for that, the way they control how much power your engine has is by, on a gas engine, they put a throttle plate. What's the throttle plate do? It restricts the airflow. What happens when you restrict the airflow? You have to pull against the vacuum to bring the piston down all the time. On diesel, the only way you're going to get it to come up to temperature enough is if you have a full charge of air in there all the time. So the diesel has no throttle. It doesn't pull against a vacuum at low power loads. So it's just free breathing, and then they close it, and then it comes all the way up. And then instead of controlling the mass of air-fuel mixture by reducing the pressure with having those restrictions, that's essentially, if you block it here and you cause this volume to happen, it's going to stretch out the charge and it's going to become less dense, less pressure. You control the mass in here by making it a vacuum. So they have manifold vacuum. Anyone ever like have a car that has the gauges, so they'll actually measure when you're idling, it'll be at like, I mean, it's a hippie-inducing vacuum. And when you go full throttle, it kind of comes up almost to atmospheric pressure. If you get supercharger, it'll go above atmospheric pressure on the inlet manifold. But it's always like, but diesels tend to be either free breathing or more commonly turbocharged. So this comes in with a bunch of air. It might even be pushing the piston a little bit. The backside of the piston's atmospheric pressure, and the intake's 10 psi or 5 psi or something like that, then it's going to actually help push the piston. Then you get a full charge of air, and now you squeeze it, and when you squeeze it, it gets hot enough to cause the fuel to burn. And so with the diesel, instead of setting off the spark, they have a timed injection, direct injection of fuel. Diesel oil is basically crummy kerosene. So you spray kerosene in there, and as you spray it in there, it starts to burn. Actually, it comes in relatively cold. I mean, it's probably not cold, but it's not burning. It comes in, it takes a little bit of a delay, and then while it's warming up, it's mixing with air, and when it finally gets hot enough, it starts to go. If you ever hear like the diesel, the sort of the rattle, there's sort of this pre-ignition phase, and then I forget what to call that. But basically, when there's enough fuel-air mixture that it will burn, enough air to burn the fuel, that one will pop. And then the next thing that happens is you have mixing controlled combustion, where as the rest of the air mixes with fuel that's unburned, then it burns. And they burn relatively slowly after the pop. Gasoline burns faster. So that's conceptual difference in how they operate. This might have 8-to-1 compression. This might be, needs to be more like 18-to-1 to work, sometimes 20-to-1. And remember on ideal gas, or on the Otto, the whole efficiency was, the theoretical efficiency was limited by just about compression ratio. That was all that really mattered. Same here. The diesel, that's the Otto cycle. And now this is all modifying that. In theory, this makes it less efficient than the Otto cycle. This makes this term get bigger, which makes it smaller, the efficiency smaller. But in reality, this number can be so much bigger that this modifier doesn't, it still comes out better. So remember I said depending on how much power you want, depending on how much you squirted, squirt more fuel to get more power, burns more or whatever. That has to do, so the diesel cycle is same isentropic compression, but instead of going this far, it goes more. It goes from more compression. And then when it gets to that point, they inject the fuel. Depending on how much fuel they inject, they model it as a constant pressure expansion. So as the piston's moving, it's burning and pushing, keeping the pressure up. And when the fuel stops burning, then the pressure drops. And the difference between this volume and that volume is what they call a cutoff volume. So the fuel cuts off the pressure, and that volume difference, basically, that's what this C is about. And that's, so if you're just idling, that value is going to be really small. If you're full power, then that value is pretty big, and that affects your efficiency, theoretically. So there's one more term we've got to deal with, not just a compression ratio, but now the cutoff ratio, which means that our expansion beyond that is going to be, it complicates a little bit, but it's not just expanding, it's the compression ratio. It's got an expansion ratio is different from compression ratio according to cutoff, how much it expanded before it started doing isentropic thing. So we'll talk about that more next time.